This screencast is on how to calculate the pH of a buffer solution. A buffer is classified as a weak acid and a salt of that weak acid, or a weak base and a salt of that weak base. So this is the situation that we have right here, where I have my weak acid, which is acetic acid, and then I have my salt of that weak acid. It has that acetate ion. This is going to be basically the same thing as that common ion effect, where we have some common ions. In this case, it's going to be acetate, which is going to slow down the ionization here of this acid. So what you want to do is you want to take the weak thing. In this case, it's going to be that weak acid, acetic acid, and we're going to show how that thing splits up in water. So in water, it is going to give off hydrogen ions and acetate ions. Now we're going to make our icebox. And initially we have 0.5 molar here. Before any ionization happens, we have no hydrogen ions. We do have some acetate ions, and that comes from sodium acetate. Sodium acetate is going to split up into sodium ions and acetate ions, and it's a 1-to-1 mole ratio. So if the concentration of sodium acetate is 0.25, then the concentration of the acetate ions floating around in solution is 0.25. And that's really the only trick right there. Proceed with the icebox the exact same way as you would before. So once it starts interacting with water, we're going to get more ionization. How much? I don't know. So we're going to make that x. So this is going to be x. This is going to be 0.25 plus x. And this is going to be minus x. So this is going to be 0.5 minus x. All right. Now we can put that into our equilibrium expression, where Ka is going to be equal to hydrogen ions times acetate ions over my acetic acid concentration. And we know that given in the problem, 1 times 10 to the negative 5 is the Ka for acetic acid, and now it's going to be x times 0.25 plus x divided by 0.5 minus x. X is going to be small in relation to these other numbers because our acid ionization constant is pretty small. So x is tiny. We can cancel those out, and then we're going to find that x equals 3.6 times 10 to the negative 5. Now x, what I'm interested in is the hydrogen ion concentration, so that is my hydrogen ion concentration there, and then to find the pH, I just need to take the negative log of that. We know it's going to be lower than 5, so 4 point something, and in this case it ends up being 4.44, there with 2 sig figs after the decimal. There is another way to calculate the pH of a buffer solution. Now you can only use this with buffers, but it's kind of a shortcut. It's called the Henderson-Hasselbalch equation. And this is what the Henderson-Hasselbalch equation looks like. So we can do it this way or this way. pH equals the pKa. All right, so just like pH is the negative log of the hydrogen ion concentration, pKa is the negative log of the Ka plus log of our ion, whatever that ion happens to be. In this case, it would be acetate, over the concentration of the weak acid. In this case, it would be our concentration of the acetic acid. So for that one, our pH is going to equal negative log of 1.8 times 10 to the negative 5. That gives us our pKa plus the log of my acetate ion concentration, which is 0.25 from that sodium acetate.
Please, with the following students, please come to the office.
All right, so this is my concentration of the common ion. So this came to us from the sodium acetate over the concentration of that weak acid, which was 0.5. You plug all this into your calculator and you get the pH equal to 4.44, the exact same answer that we had before, just to prove that it worked.